Section 1. Introduction. Deconstructing the SN2 paradigm. In this video, we embark on an exhaustive exploration of one of the most elegant and fundamental transformations in the lexicon of organic chemistry, the SN2 reaction. To truly master the predictive power required for complex synthesis, we must first deconstruct the nomenclature of the SN2 label. The S denotes substitution, a conceptual framework where one functional group, the leaving group, is displaced by another. The N signifies nucleophilic, identifying the attacking species as nucleus-loving, an electron-rich entity seeking out a positive, electron-deficient center. The numeral 2 is perhaps the most critical component, as it describes the bimolecular nature of the process. In the realm of chemical kinetics, this indicates that the rate-determining step involves a simultaneous collision and interaction between two distinct molecular species. When we derive the rate law empirically, we observe that the reaction velocity is directly and linearly proportional to the concentration of both the substrate and the nucleophile. This second-order kinetic behavior is a profound window into the molecular event. It dictates that any modification to the concentration of either reactant, be it the electrophilic alkyl halide or the attacking cyanide ion, will have a one-to-one impact on the overall rate. Section 2. Reaction mechanism. The concerted electronic dance. Let us visualize the sub-microscopic dance of the atoms. The SN2 mechanism is defined as a concerted process. In the language of physical organic chemistry, this means the reaction coordinate contains no intermediate energy minima. There are no reactive intermediates, no carbocation ions, and no carbon ions. Instead, the formation of the new bond and the cleavage of the old bond occur in a single, synchronized and fluid motion. As the nucleophile begins its trajectory toward the electrophilic carbon, its highest occupied molecular orbital overlaps with the lowest unoccupied molecular orbital of the substrate. As electron density is pushed into the carbon center, the bond between the carbon and the leaving group begins to polarize further, weakening and stretching. This continuous transformation culminates at the transition state, the energetic zenith of the reaction. At this fleeting micro-moment, the carbon center is effectively pentacoordinate. It temporarily abandons its sp3 tetrahedral geometry to adopt a trigonal, bipyramidal-like arrangement. The three non-reacting substituents, often called spectator groups, migrate into a single equatorial plane, forming 120-degree angles with one another. Simultaneously, the incoming nucleophile and the departing leaving group align themselves 180 degrees apart along the axial positions. Notice the development of partial negative charges. As the nucleophile shares its charge with the carbon, and the leaving group pulls electron density away, the negative character becomes delocalized across the axial system. This delocalization is what allows the transition state to exist, albeit for only a femtosecond. On an energy profile diagram, this appears as a single, smooth peak. Crossing this barrier represents the point of no return. The umbrella of substituents flips, the leaving group departs with its bonding pair of electrons, and the new nucleophile carbon bond is finalized. Section 3. Stereochemistry, Orbitals, Symmetry, and Walden Inversion. Before we dive in, a quick note on the 3D models used in this video. To maximize the visibility of MO interactions, the atomic radii have been further reduced to 25% scale. For our demonstration, we will be using 2s2-bromobutane as the substrate and iodide ion as the nucleophile. To aid your understanding, we have rendered the HOMO and LUMO of the CBr bond as 3D models. The sigma bonding molecular orbital, or HOMO, is shown as a continuous, in-phase electron cloud spanning the space between the carbon and bromine nuclei. In contrast, the sigma star and tie bonding molecular orbital, or LUMO, clearly displays a nodal plane between the two atoms, with its lobes pointing away from the bond axis. A defining feature of the SN2 pathway is the mandatory backside attack. But why must the nucleophile approach from directly opposite the leaving group? The answer lies deep within molecular orbital theory. For a successful reaction, the nucleophile's lone pair must donate electron density into the lowest unoccupied molecular orbital of the substrate, specifically the sigma star antibonding orbital of the carbon-leaving group bond. Due to orbital symmetry, the largest lobe of this sigma star orbital, the region most capable of accepting electrons, is located precisely 180 degrees away from the leaving group. This allows for an in-phase interaction, leading to constructive orbital overlap that initiates bond formation. In contrast, a frontside attack would result in an out-of-phase interaction, which is antibonding in nature. Owing to orbital nodes and strong electronic repulsion from the electron-rich leaving group, any potential overlap here would be destructive and negligible. As the nucleophile populates this anti-bonding orbital, it effectively destroys the carbon-leaving group bond. The resulting geometric strain forces the remaining three substituents to invert their spatial orientation, a phenomenon known as Walden inversion. It is the molecular equivalent of an umbrella being blown inside out by a powerful gust of wind. If the reaction begins with a stereochemically pure enantiomer, the SN2 mechanism will deliver the product with complete inversion of configuration. This process is essentially stereospecific, ensuring that the spatial arrangement of the atoms is predictably reversed. Note that while the configuration is always inverted, this does not always mean a change from R to S. It depends on the priority of the incoming nucleophile relative to the other substituents. Section 4. Substrate effects. The energetic wall of steric hindrance. To better understand the role of steric effects, we will now transition to a van der Waals sphere model. This perspective yields deeper, more intuitive insights into steric hindrance. SN2 reactivity depends on a clear backside path. When bulky groups crowd the substrate, steric hindrance takes over. These groups shield the carbon center, effectively blocking the nucleophile's access to the required orbital overlap. To quantify this effect, we've set the relative rate of a secondary substrate as our baseline of 1. First, we have methyl substrates. With only tiny hydrogens surrounding the central carbon, there is virtually no hindrance, allowing them to react extremely rapidly. Moving to primary substrates, the reaction center is still quite accessible, though you'll notice a slight decrease in speed compared to methyl. The shift becomes much more dramatic with secondary substrates. Here, the reaction slows down significantly as steric congestion increases and the activation energy begins to rise. Finally, tertiary substrates are essentially inert toward SN2 reactions. In this case, the three bulky alkyl groups form an impenetrable steric shield, making it physically impossible for the nucleophile to reach the target. We even observe neighboring effects. Neopentyl bromide, though technically a primary substrate, reacts extremely slowly because the adjacent tertiary butyl group blocks the nucleophile's approach path. In SN2 chemistry, space is the most valuable currency. Section 5. The nucleophile. Kinetic power versus thermodynamic basicity. Because the nucleophile appears directly in the rate law, its strength has a direct and measurable impact on reaction speed. This property is known as nucleophilicity, a kinetic measure of how rapidly a species attacks an electrophilic carbon. First, let's consider the charge effect. In the SN2 landscape, negatively charged species are consistently more powerful nucleophiles than their neutral conjugate acids. Take the oxygen center as an example. The methoxide ion, with its high electron density, is far more nucleophilic than neutral methanol. A full negative charge simply provides more kinetic punch to initiate the attack. A common pitfall is confusing nucleophilicity with basicity. While they often trend together, they represent two different chemical realities. Basicity is a thermodynamic property, a measure of how strongly a species binds a proton at equilibrium, often quantified by pKa. Nucleophilicity, in contrast, is a kinetic property, describing how rapidly a species attacks an electrophilic carbon. When comparing atoms within the same row of the periodic table, nucleophilicity and basicity are intrinsically linked. Let's break down why this correlation exists by following the data. First, we look at the conjugate acids of our nucleophiles: water for the hydroxide ion and ammonia for the amide ion. While water has a pKa of 15.7, ammonia's pKa is significantly higher at 35. This tells us that ammonia holds onto its proton much more tightly than water does. Based on these values, we apply the fundamental rule. The higher the pKa of the conjugate acid, the stronger the resulting conjugate base. Therefore, the amide ion is a far more powerful base than the hydroxide ion. Because a stronger base has a higher tendency to share its electron pair, this increased thermodynamic drive translates directly into a faster reaction rate. In this specific context, basicity and nucleophilicity follow the exact same trend. However, these trends can diverge dramatically depending on the environment. In polar aprotic solvents, nucleophilicity follows basicity. But in protic solvents, the order is completely reversed. Here, smaller, more basic ions like fluoride are hindered by a tight solvation shell of hydrogen bonds, while larger ions move more freely to reach the substrate. This brings us to the power of polarizability. Large, soft ions like iodide possess diffuse, easily distorted electron clouds. Unlike hard basic ions, iodide can begin forming a bond from a greater distance through constructive orbital overlap. This makes it an exceptional nucleophile, even though it is a very weak base. Finally, we must account for steric bulk. Bulky bases, such as tert butoxide, are chemically paradoxical. They are structurally strong bases, but notoriously poor nucleophiles. Their massive methyl groups create a physical barrier, making it impossible to achieve the precise backside attack required for SN2. Section 6. Solvent effects, freeing the naked nucleophile. The reaction medium can alter an SN2 rate by factors exceeding 1 million. To maximize SN2 efficiency, chemists employ polar aprotic solvents such as DMSO, DMF, HMPA, or acetone. Protic solvents, such as water or ethanol, contain OH or NH bonds capable of strong hydrogen bonding. These solvents tightly solvate anions, forming a stabilizing solvent cage around the nucleophile. For reaction to occur, the nucleophile must escape this cage, which requires significant energy and dramatically raises the activation barrier. Polar aprotic solvents, in contrast, can dissolve ionic species without hydrogen bonding to the nucleophile. The anion is left relatively unsolvated, or naked, and therefore much higher in energy. Because the starting point is higher, the energy gap to the transition state is smaller. Simply switching from methanol to DMF can transform a reaction that takes days into one that finishes in seconds. Section 7. The leaving group, stabilizing the departure. The final variable in our SN2 equation is the leaving group. While the nucleophile initiates the attack, the reaction's progress depends on how effectively the leaving group can depart with its bonding pair of electrons. In the transition state, as the carbon-leaving group bond stretches, a partial negative charge develops on the exiting group. Therefore, the best leaving groups are those that can most effectively stabilize this developing charge. This stabilization is typically achieved through a large, polarizable atomic framework that disperses electron density over a greater volume, as seen with heavier halides. Alternatively, electronic effects such as resonance can be utilized to delocalize the negative charge across multiple atoms. A fundamental principle in organic chemistry is that the weakest bases make the best leaving groups. We can quantify this by examining the pKa values of their conjugate acids. Strong acids have weak, highly stable conjugate bases, which in turn function as exceptional leaving groups. Consider the halides. Iodide is the conjugate base of hydrogen iodide, a very strong acid. Because iodide is a weak, polarizable, and stable base, it is an excellent leaving group. In contrast, fluoride is a relatively stronger base, making it a poor candidate that rarely participates in SN2 pathways. Beyond the halogens, chemists frequently utilize sulfonate esters, such as the tosylate ion. Through resonance, the negative charge is delocalized across 3 oxygen atoms, providing the immense electronic stability required to lower the activation energy by stabilizing the developing electrons in the transition state. By choosing the right leaving group, we can effectively lower the energy barrier and control the success of the SN2 reaction. Now, let's bring it all together with the SN2 strategic checklist. To conclude this masterclass, let's synthesize our findings into a 4-point strategic checklist to ensure the success of any SN2 reaction in the laboratory. First, minimize steric hindrance at the reaction center. The hallmark of the SN2 mechanism is the backside attack. Methyl and primary substrates are your ideal candidates. Once you move to secondary substrates, the reaction rate drops precipitously, and at the tertiary level, SN2 becomes physically impossible. Second, ensure the kinetic power of your nucleophile. You must choose a strong, polarizable species. Use anionic reagents such as hydroxide or cyanide, and ensure they are sterically unencumbered so they can effectively penetrate the sigma star orbital of the electrophilic carbon. Third, liberate your nucleophile with the right solvent. Protic solvents, such as water or alcohols, cage your nucleophile through hydrogen bonding, stripping its reactivity. Always employ polar aprotic solvents like DMSO or DMF to create a naked nucleophile, drastically lowering the activation barrier. Fourth, optimize the leaving group efficiency. The leaving group is the key to lowering the energy of the transition state. Excellent leaving groups, such as iodide or tosylates, are weak bases that can stably carry the developing negative charge as they depart. By precisely manipulating these 4 variables, you gain total command over both the reaction kinetics and the stereochemical outcome, specifically the Walden inversion. Mastering this checklist is how an organic chemist truly directs the flow of electrons in synthetic design. To wrap up, take a moment to examine the relative reactivity charts for leaving groups and nucleophiles. Understanding these relative values is key to mastering synthetic design. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.